Okay, so we can start with our e to the I x, just to refresh our minds where we started. We started from this guy, which is I to the x to the n factorial, and n equal 0 to infinity, which we chop down up to n large enough. And then we say, and this is divided in 2 bits, which are the sinus of x and the cosinus of x, with an I in between, because these are the sum of minus n x to the 2n divided 2n factorial plus I, the sum of minus 1 to the n x to the n plus 1 divided 2n plus 1 factorial. Okay, great. So we have our two functions, and this is our exponential of the complex number. So now we remember just one simple thing, that I say that again: when you multiply a number 1 by I, you basically do a rotation by 90 degree, pi over 2, and you get minus I. And if you keep applying I to a number, you, as here many times, you keep rotating your number, basically you keep rotating your number up until you get your z value with an angle x. Okay, so something very similar happens when you have vectors in real space. So r times r, so it's not the complex space, these are real numbers and real numbers, and we're dealing with vector, as we did already in our vector video. So this is vector 1, 0, and then if you apply this matrix A, which we already encountered, okay, this matrix A here, we see that the rotation is the same as in the complex number with minus I, just you end up in the vector 0, 1. And this is because if you do 0, minus 1, 0, 1, 0, you easily get 0, 1. We know that by computing this product matrix time vector quite easily. And if you do it another time, you get to the vector minus 0, 1, 1, 1, 0. Which means that a square, the square of the matrix, is minus the identity. Okay, very much like I times I is equal to minus 1. But also we get that minus, we get a cube. If we apply another time, we get a. In fact, minus a. In fact, if we multiply this by basically twice, we get minus identity, which is minus 1, minus 1. But if we multiply it by another time, the same matrix A, okay, and this is 1, we get exactly minus 0, minus 1, 1, 0, minus A. We can do the multiplication, and we can get this equation here. From these two simple facts, we can easily check. Now the computer is stuck. Yes, so we can easily check that if we apply an even number of times a, we get minus n the identity, and if we apply an odd number of a, we get minus 1 to the n a. This is very much like what we did here, right? with the minus odd and even power. The only thing that changes is that now we will be able to sum these two components because we are dealing with matrices and not with complex numbers with the imaginary part. So we will get a different result in the end, as I will show you. And what I want to say is the following. Let me erase what I don't need, which is this and this. It's a bit slow because I'm always loading the other video. Okay, so what I want to say is the following. The only thing that we need to remember is that we can sum two matrices to get another matrix, and to do that we just do element by element. Yes. So I will leave it here. So we remember that the sum of matrices is another matrix with the component by component, with the sum component by component. And easily we get x to the a is xa plus b plus xb, sorry, not plus xc, xd. It's a matrix, so there is no plus there. I mean, it's the sign of the number, but it's not a sum of the two numbers. So let's write this correctly. And this is the standard way to multiply a matrix by numbers. You multiply each component by a number. Okay, so now down to business. When we have this expression, which by no surprise is written as usual because it's an exponential, we can chop it in two pieces because of these two equations. So actually these two equations down there, and we have sum over n, and goes from 0 to minus 1 n x to the n divided to the n factorial identity, plus the other bit is sum. There is no I this time. There is always this odd coefficient and x to n plus 1, but this time there is a, not I but a. Okay, now we do a step further because we can recognize that this function and this function here is the same that we have up here, which are sinus and cosinus are the same. Therefore, we can write cosinus of x times identity plus sinus of x times a, because that's the matrix is just a multiplicative factor in front of it. So we do component by component, the multiplication of a matrix by a number. So we get cosinus of x 0, 0 for the first bit, plus we get 0 minus sinus of x, because remember a is equal to 0 minus 1, 1, 0, and this is sinus of x 0. Okay, now we are almost done. We just need to do the sum component by component as is written here. So we can just erase this bit and erase this bit because we are summing component by component, and we get minus sinus of x sinus of x, which is exactly the same rotation matrix that we derived last time in the matrix video. Okay, so this is the conclusion of the matrix exponentiation. We can do a bit more. With this, we will see that matrix exponentiation plays a role in physics as well, in some famous equation, but we will get to that. For now, it's okay. I hope you enjoy. See you next time.